Welcome to this video on central limit theorem. By the end of this video, you should be able to explain how the shape of a sampling distribution of a sample mean is affected by the shape of the population distribution and the sample size. And if appropriate, you should be able to use the normal distribution to calculate probabilities involving a sample mean. Alright, so our scenario today is who has better ACT scores, Etowah or Woodstock? So the ACT score is scored with whole numbers from 0 to 36. So we're going to use this applet, and I'll pull this up so you can watch it, to take samples of ACT scores from Etowah and Woodstock. Alright, so we are going to click Begin, and we have this shape here. I want you to take a second and describe the shape, the center, and the variability. Alright, so for our shape, as you can see, it comes up and down. It's really nice and symmetrical. I went ahead and put approximately normal for shape. Now the center, if you noticed right over here, the median, which will be the center, and the mean, there's 16, because in a normal distribution, the mean and the median are the same. So for my center, I have 16. And my spread, it says right up here the standard deviation is 5. So for my variability, I have 5. So I just want you to remember some notation. You don't want naked numbers, so make sure you use the appropriate notation to say what these are. Okay, so now I'm going to click the animated button, and I'm going to take a sample of 5 ACT scores for us to see. Okay, so this top one here, this is our population. I'm going to take a sample of 5, so there's my 5, and then from these 5, we got the average of those 5, and that dropped down here. So this is a distribution of a single sample. This is a sampling distribution of a bunch of samples. We've just only taken one so far. Okay, so let's take a look at our numbers. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like we have 10. And then 11, 12, 13, 14, 15, 16. 17, 18, 19, 20, 22, 23, 24, 25, and 26 was our sample. Alright, so take a second to get this mean. Well, hopefully that doesn't actually represent our Etowah students. That's a pretty low mean for an ACT score. 10.9 is what I got. Alright, so now what I'm going to do is I'm going to click the animated button a few more times to give you an idea of how we're going to take a sample at the second one, a sample of 5, and then the average from those 5 is going to drop down here. So here's a second sample of 5, and there's the mean of that 5. Another sample of 5, and the mean from that 5. Okay, so this is one sample. And this is the aggregate of all the averages of those individual samples of 5. Okay, so the blue dot is one sample of 5 who has a mean of whatever this number is. Okay, so let me do 10,000 of those. So it would have dropped 5 samples over and over and over, and then the average of those 5 samples, and we get this. Okay, so we have this distribution. The blue boxes are making the sampling distribution of X bar. How do we know the sampling distribution of X bar is approximately normal? Hint, see the previous lessons. So look at yesterday's summary and see if there's something in there that will help you answer this question. Pause the video and give it a try. Alright, so in our previous topic for sample means, we had said if the population distribution is approximately normal, so is the sampling distribution. So in this case, our population was approximately normal, so our sampling distribution of X bar is also approximately normal. All right, so that was Etowah's ACT scores. Now I want to look at Woodstock's ACT scores. All right. So I'm going to clear this and I'm going to change this. Here's Etowah's, and this is Woodstock's scores. Okay. So why does this distribution make sense for our arch rival Woodstock? Why does it make sense? Here's why. You have a large number making low scores and only a few who are making higher scores. So naturally I'm saying I think we're so much smarter. And so that's what this question is asking. So that's what we want to write here, is that the distribution is skewed right. And it makes sense because most students will do poorly, only a few will do well. You know, compared to Etowah, we're going to perform better, but we'll see. All right, so what I'm going to do is I'm going to change, we're going to talk about sample size here. Okay, and see what your sample size does to your sampling distribution. All right. So I'm going to change this to a sample size of 2 and this one to a sample size of 25. All right, and now I'm going to take 10,000 samples. So when I take 10,000 samples with a sample size of 2, I get a slightly less skewed distribution. So let's take a look at number 5. So let's describe it for number 2. Take a second to do that. Okay, so we said for when n is 2, it's skewed right, but not as strongly as the population. Now let me go ahead and try this here for our sample size of 25. Also, look what's happened. This is a sample size 2. It's spread a lot, but not as much as the population. It's still skewed, but not as much as the population. We go to a sample of 25, its spread is much smaller, its variability is much smaller, and now its shape is approximately normal. Okay, so now with a sample size of 25, we got a shape of approximately normal. And the reason for that is when the sample size is large enough, this sampling distribution is approximately normal. Again, when the sample size is large enough, the sampling distribution is approximately normal. So what do we mean by large enough? We've talked about this periodically throughout the course so far. Large enough would be if your sample size is greater than or equal to 30. Now, this number isn't the magic number. There is some other things that play into it, but we're just always going to compare our sample size when we're doing the sampling distribution of X bar to 30. It's kind of like a rule of thumb. And so, and what we call this is called the central limit theorem. So there are conditions that we have to prove. Remember when we were doing the sampling distribution of X bar in the previous video when we were finding our standard deviation of the sample, in order to use that standard deviation formula, your 10% condition must be met. And so that was one of the conditions we have to check. For your distribution to be approximately normal, it has to meet the central limit theorem, and so you have to cite this, but you don't have to write central limit theorem. You can just write CLT. That's an acceptable abbreviation for this theorem that's well known and would not require defining for your reader to know what that is. Okay, so what we did is we started by looking at the population of Woodstock students that was skewed right. So this up here was our population distribution. And from that, we created two different sampling distributions. So both of these were sampling distributions because they represented a bunch of different samples. This, the question from number 5 represented a bunch of samples of size 2. It still remains skewed, just not as skewed as the population, but once we got up to a bigger sample size, so here we didn't even hit that n is greater than or equal to 30, and we were able to achieve an approximately normal. So there's a lot of factors in play, but we're going to use the central limit theorem and the n is greater than or equal to 30 to justify approximately normal, so we can use normal calculations to determine probabilities. All right, let's flip this over and take a look to see what we need to summarize down. All right, so I have two things I want to be sure you take away, two big topics. The first one is our central limit theorem. And that central limit theorem says the sampling distribution of x bar is approximately normal when the sample size is large enough, and we're using a rule of thumb of n is greater than or equal to 30. If you're reading in your book, I believe your book says 35. Either is acceptable. We're going to go with 30 in class in all of our notes. Now this is only for sample means. When we talked about approximately normal for proportions, that was our large counts. So we have to remember the difference when talking about normal. For proportions we use large counts, which was the n times p has to be greater than or equal to 10, and n times 1 minus p also has to be greater than or equal to 10. That would tell you approximately normal for proportions. For means, it's going to be the central limit theorem. Okay? All right, the other one is your normal calculations. I keep repeating this because it's pretty important. It's a big basis of what we'll be doing. So our normal calculations for the sampling distribution of x bar okay, and so this is the sampling distribution of x bar. Okay, right down the middle you'll have your mean, which will be equal to the population mean. You're going to note that it's a normal distribution with a mean mu and a standard deviation of the population standard deviation divided by the square root of n. Then you'll want to be sure you mark whatever your score of interest is and do the shading. Remember that it's as extreme or further from the mean. So if our numbers on the right of the mean, it's from the x bar up. If our numbers on the left of the mean, it's from x bar down, because we're going as extreme from the mean. And your formula where you would get the numbers is this would be whatever that score x bar is that you're interested in minus mu divided by the standard deviation of the sample, and then you use table A. All right, so what I want you to do is I want you to try this, check your understanding. And I have the key on Canvas, but really, 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 please, I want you to try to do these on your own and then use the key to verify that you've either got it or you need to check in on something because you don't understand it, so you need to contact me about it. If you just copy what I've got written down, it's not really benefiting you unless you understand why you got something wrong. So please try it first. Check your answers on Canvas. I'm really looking forward to seeing people in class again.